In Chapter 13, we begin discussing the concept of equilibrium for chemical reactions. We will be using this concept for the remainder of our semester as we discuss the process of reactions happening in both directions. The opening screen for this chapter shows carbon dioxide moving through tissues and blood cells and setting up equilibrium as it reacts with water to make hydrogen carbonate. And you'll notice these new arrows that we're going to use that show equilibrium, indicating that a reaction is happening in both directions. As an example of the concept of equilibrium, if you were going to do a load of laundry and dry your clothes outside, would they dry faster in a hot and humid environment or a cold and dry one? And in fact, clothes would dry faster in a dry environment, and that's because there are less water molecules in the atmosphere. And so as the water from the clothes is released into the atmosphere, they'll do that faster in a dry environment. We typically think about drying clothes being related to temperature, but that's just because our clothes dryers use heat as the mechanism to speed up the drying process. When we discuss chemical equilibrium, it's important to realize that not all chemical reactions will go to completion. In first semester chemistry, you likely did an experiment where you had to calculate a percent yield, and it's very rare to get 100% yield. And it's not necessarily because of lab or what you did, it's because of the reaction itself. Every reaction will achieve a state of equilibrium. And most reactions are reversible, meaning they will react in both directions. For a lot of our examples in this chapter, we're going to use this reaction, the decomposition of dinitrogen tetroxide into two NO2 molecules. And notice the new arrows we're using here. So these arrows specifically illustrate the concept of equilibrium, that this reaction is happening in both the forward direction, so that top half arrow shows forward, and then the bottom reverse arrow showing that this reaction is also happening in the reverse direction. There are two definitions we can use to identify when or how equilibrium has been reached. The first one is the most relevant, and this is the one that we'll refer to for the remainder of our semester. Equilibrium is reached when reactant and product concentrations or pressures, whatever unit we're measuring for amounts of substances, no longer change. And on the next slide, I'll illustrate this with a graph. It does not mean that reactant and product concentrations are equal to each other. So it just means that we no longer see a change in amounts of substances. The second definition of equilibrium refers back to rates from our kinetic chapter. And this definition states that equilibrium is reached when the rate of the forward reaction equals the rate of the reverse reaction. We'll only use this definition as a way to derive our equations that we use for equilibrium. On this graph, or on this slide, I want to illustrate a graph identifying how we know when equilibrium has been reached. So again, I'm going to use our first equilibrium equation, the decomposition of N2O4. And so remember from kinetics, we could plot time on the x-axis and concentration on the y. Since N2O4 is shown as a reactant here, I would begin with some amount of that and of course have it decrease over time. And what we didn't carry through in the kinetics chapter is what happens when our rates no longer change. So realize that about at this point where that vertical dotted line is, this is the point when we notice that our graph has leveled off. It has become completely horizontal. Our concentration of that substance is no longer changing. For my NO2s, of course, that's going to increase fairly steeply because it has a higher coefficient. And notice that I've tried to illustrate here that again at that dotted line is about when the concentration of that substance no longer changes. So again, this curve that's increasing is showing our NO2. So realize the amounts of NO2 and N2O4 are not the same when they've leveled off, but the concentration of each one no longer changes. A few other key things to remember about equilibrium is that it is a dynamic state. So although the concentrations are no longer changing, both the forward and the reverse reactions are still happening. They're just happening at a rate at which we don't see a change in any of our numbers. No concentrations or pressures are changing. So if we were to take measurements, it would look like the reaction has stopped, although it hasn't. And equilibrium will be reached for every reaction, and it can be reached starting with just reactants, which is the most common scenario that we'll discuss. We could start just with products, though, and still have equilibrium be reached. Or we could start with a mixture of reactants and products and still have equilibrium be reached. One of the key things that we'll discuss as we go through this chapter is that at a given temperature, the ratio of products to reactants will always be the same. It will be a constant. And remember from kinetics, our rate constants were constant at a given temperature. We have the same idea here for chemical equilibrium. So they're a constant at a given temperature. Once we change temperature, the value of the constant will change. So a little prettier graph here, again showing our same decomposition reaction. And this one is showing that if we start with N2O4, right, we're starting with a concentration of that. NO2 is our product. It starts at 0. Again, realizing this vertical line here is illustrating when chemical equilibrium has been reached. So again, these concentrations have leveled off and are no longer changing. So that is starting with N2O4 as a reactant. In this graph, notice that the difference here, we have the same chemical system, but in this one, we actually put NO2 in our container first and allowed this system to come to equilibrium. So we still write the reaction or the equation the same way, but in this case, we're actually starting with products. Again, notice it takes about the same amount of time for the system to reach equilibrium, and we can tell it's at equilibrium because those concentrations have leveled off and are no longer changing. To make sure the idea of equilibrium makes sense, I want you to take a minute and look at these three systems. So we have system 1 up top, then 2, and then 3. And I want you to identify which of these three systems took the longest to reach equilibrium. So take a minute, pause the video. When you have an answer, replay, and then we'll come back and discuss the answer. All right, so I assume you have an answer. So for this one, realize that at time 0, we're starting with these blue reactant molecules in each system. And as the reaction proceeds, we're starting to form the purple products. So remember, equilibrium is reached once amounts no longer change. In reaction system 1, realize that equilibrium has been reached by T2. Because as I look at T2 versus T3, I see the same amounts of substances in these. And so T2 is when the system reached equilibrium. For reaction system 2, we do the same thing. However, notice that as I compare T2 to T3, these two boxes, there's still a change in number. So in this one, my system might or might not have reached equilibrium yet. So possibly at T3 it's at equilibrium, but it could still be changing, so maybe later. So let's look at reaction system 3 and see what happens here. Again, notice in this one, if we compare the amounts of substances in T2 versus T3, they're the same. And so that means that this system reached equilibrium at T2, at time 2. And so our reaction system 2 took the longest to reach equilibrium, whether it was at time 3 or later.